Now let's take a look at example number 6. We're going to try to prove that this integral listed here is indeed convergent. Now, notice that because it asks me to show that it's convergent, that doesn't require that I find a final value, right? I don't need to know what the area is, just if it's finite or if it's divergent. So because of that, that's going to open up a lot of additional options. Now we saw this curve here in the last section, and so I'm going to go ahead and provide a rough sketch of what that curve looked like. It looks something like this. And here, again, we're interested in finding the area from 0 off to forever. That's our objective, from 0 onward. So what I'm going to go ahead and do here really quickly are just a couple of things that at first glance may seem unnecessary, but bear with me for a moment. I'll start off by saying that we see that if I wanted to do an integral from 0 to infinity of e to the negative x squared, I could easily separate that out into an integral from 0 to 1 under that function, and then add on the rest of the integral from 1 to infinity. Now again, this may seem kind of strange. Notice what I'm doing is I'm kind of dividing up my integral into two pieces. Now of course this first piece over here I know is definitely going to have a finite amount of area, right? I mean, it's even finitely bounded on the page. But this other area, we don't really know if that's going to be infinite or not infinite, right? That is, we don't know how much area it's going to have. So what we can see is that if I can determine whether this integral is convergent or divergent, I kind of have an answer to the question. If this integral is finite, convergent, then two finite things added together make a finite thing. And if this integral is divergent, or maybe infinite, then adding on something finite to it won't change it from infinite. So because of this, I'm going to focus on this integral specifically. I'll write this as, we need to find the integral of this, and then the question is answered, since our integral from 0 to 1 is finite. Okay, so let's go ahead and think about how we're going to determine this integral. Our goal is going to be to use the comparison theorem. We want to know or see how we might be able to make e to the negative x squared into either a red g of x function or a blue f of x function. Now we don't really know which one we would want to have here at first. We might be able to guess based on the fact that we have a convergent result. But I'm going to go ahead and show you how I would try to work through this question if I wasn't told what the result that I was shooting for was actually going to be. Right? If I wasn't told the integral was convergent, how would I proceed? Well, I'm going to go ahead and start here by focusing or zooming in on this integral. Okay, so let's see. I'll say since x is in the interval, closed interval on this one side, closed from 1, open off to infinity, then I can start to make a couple different deductions. Hopefully you would agree with each of the following moves. Notice these are moves that specifically work for the interval 1 to infinity, but not for the interval 0 to infinity. At least not all of these moves. First, hopefully you would agree that x has to be greater than or equal to 1. Seems pretty basic, right? But of course, once I have that, I can state that if I multiplied both sides by x, x squared would have to be greater than x. Notice that that's not necessarily the case if I'm going to be working with numbers in the interval 0 to 1. So this is the reason why I actually split this up. Notice this doesn't work for a statement like a 1/2. 1/2 squared is a quarter, and a quarter is not larger than a half. So once I'm here though, and I know that this works with values that are greater than 1, now I can go ahead and quickly see that I can make one more manipulation. Wouldn't you agree that if I took negative x squared and negative x and compared them, that my inequality sign would have to flip? It's like I multiplied everything by a negative. And now I'm going to go ahead and pretend that both negative x squared and negative x are going to be exponents of an e. So notice I'm going to have an e to the negative x squared and an e to the negative x. Now, I can probably easily see here that the one on the left has the smaller exponent. That's what we set up above. And so definitely then it's going to be the smaller overall value. Notice what we have is our function e to the negative x squared, and we've actually found a function to compare it with, e to the negative x. In terms of the comparison theorem and the color coordination that we have, f of x, the blue function, was the larger one. So we could say down here, this is my blue function, f of x, and this right here is my red function. Well, according to the comparison theorem, let's see what happens with our blue function. I'll say we see that the integral from 1 to infinity of e to the negative x dx, this one might be able to be evaluated because it's not as tough of an antiderivative to get. I'll turn this into my limit notation, and I'll get ready to take my antiderivative. Antiderivative here is pretty simple. I'm just going to end up with a negative e to the negative x evaluated from 1 to t. Now I'll go ahead and I'll continue to write this down. I have a negative e to the negative t minus a negative e to the negative 1. Now, if I go ahead and rewrite this one more time, I'll see that this can be expressed as negative 1 over e to the t plus 1 over e, just rewriting my negative exponents. Now, the limit here is ultimately then going to just be 0 plus 1 over e, which is 1 over e. Now, I don't really care about what this limit's value is. What I care about is that this blue integral that I had up there is convergent. So my integral from 1 to infinity of e to the negative x dx is convergent. And thus, by the comparison theorem, I can easily state that the red integral, the one that has to have smaller area, would also have to be convergent. My integral from 1 to infinity of e to the negative x squared dx is also convergent. Now, some people would stop here, but I should note that I haven't really yet answered the question, because the goal wasn't to figure out if this integral is convergent, but rather if this integral was convergent. But what we just saw is that this region here in question is convergent, and if I only have a finite amount more to add on to it, then obviously I'm going to end with a convergent result. So my integral of 0 to infinity of e to the x dx, which again is equal to my integral from 0 to 1, plus my integral from 1 to infinity, this also has to be convergent, right? Because it's the sum of two convergent things. I can see here that this piece is convergent, and certainly this piece we just demonstrated is convergent. So I can actually go ahead and prove that this integral has a finite amount of area. Right, the area under this curve is finite, but I still don't know what it is. But at least I know maybe it's worth trying to find now. I know it has an answer. And so this comparison theorem is a really powerful tool to be able to help us with this. We'll see that oftentimes creating our comparisons is either going to be done by dealing with what we know about x and making these kind of strange manipulations to arrive at a red or a blue function. But we'll see in the next video that there are also some additional ways that we can try to make comparisons that'll be a bit more advantageous for us.